Dear participants, I welcome you all for this webinar. We will wait for further 2 or 3 minutes and then we will start. I will begin with introducing Naman Bajaj, today's speaker, and then I will hand over this session to Naman. Thank you. Good evening, everyone. My name is Abhishek Patange. I am currently working as an assistant professor in Department of Mechanical Engineering, College of Engineering, Pune. So first of all, I invite you all for this webinar titled Regression, Tale from Straight Line to the Random Forest. This session is handled by my own beloved student, Naman S. Bajaj. Let me introduce Naman first. So Naman has graduated with Bachelor's in Mechanical Engineering from COEP in year 2021. Owing to his overall performance during his time at COEP, he has endowed with the Institute's Best Outgoing Student Award, as well as Professor S.R. Kajale Best Outgoing Student of Mechanical Engineering Award. While at COEP, he along with his group worked under me for his minor and major projects and published various research papers in the domain of tool condition monitoring and COVID-19 regional analysis in Scopus and SCI journals. So which is really good achievement at an undergraduate level. One of his work has been published in ASME, which adds to his credibility of his research at COEP. Naman has also been passionate about astronomy and astrophysics and has consistently strived towards the same. He has had quite a glorified journey till now. He is a fellow of Royal Astronomical Society, United Kingdom, and also a member of European Astronomical Society, which is also a very really appreciable achievement at this particular level. Recently, he has also become a youngest Royal Astronomical Society member to receive a research grant. He has worked with several internationally renowned scientists in this field, including Dr. Sandel, Dr. Ripath, and Dr. Nandakumar. And he has also published his work in one of the most reputed journals of astrophysical domain. Naman is now taking his next career step of starting Ph.D. in astronomy from a reputed US universities. He has applied to multiple universities and now he is getting admit as well. So there will be one day where he will have a minimum 5 to 6 admits, and then he has to choose which university he wants to go further. So I wish you best luck, Naman, for your further journey. Now I will hand over this session to you. Thank you so much.
Thank you so much, sir. I'll share my screen. Okay, perfect. Okay, is my screen visible to all? And am I audible to all?
Yes, Naman. Yes. Naman, just a minute. Let me announce one thing. I will share the feedback link in chat box at the end of this session. So you just fill that feedback form. Don't miss to fill the feedback form because that will be used for giving you the certificates. So just remember this. Okay. Naman, go ahead.
Thank you, sir. Welcome everyone to this session that we're holding today about regression, a tale from a straight line to a random forest. We have a straight road and a random forest, and that's exactly what we are going to do today. We'll see how easy it is to fit a straight line and to regress a straight line, and how equally easy it is to fit a random forest as well. So please do not consider this as a lecture. This is a fun session, and I'll try to make it as practical as possible. And I'll be using quite a few tools, namely Davis, Matlab, Python, and Weka to perform regression on different kinds of data set that I have. So that will sort of give you an idea on which are the platforms, which are the tools that you can actually use to do this. So, and also this is quite a long session, probably 2 hours. I'll try to wrap it up earlier, but it can extend up to 2 hours. So you feel free to have your tea, coffee, soft drink, hard drink, whatever you prefer with you. And let's start. So regression. What is a regression? That should be okay. Sorry. So few important points because there can be, this is open to all, and there can be many computer science students as well as professors from various places. So this session would mostly focus on the basic types of regression, their physical explanation, and how one can implement it using various tools. So that will be my focus. The last point will always be my focus, how we can implement it using various tools. One can comprehend this session as a short overview of the need of different types of regression. Why do we need different types of regression? Like we have a we have a linear regression, but why do we need a random forest regression or a Gaussian regression or anything like that? So what is the need behind having this different types of approaches for regression? And since I'm a mechanical engineer and astronomer, as you would have heard from Patange sir's description of me, my perspective is that of applied as opposed to build. So there are, when we talk about algorithms, when we talk about all these tools, there are two groups uh, which we can classify them in. One is the group that builds the algorithms, that creates the algorithms, and the other group is the applied one, that is the one that applies those algorithms to their problems. So I'm a mechanical engineer, I'm an astronomer, but I'm not a computer scientist or something like that who would create a code. I do not create algorithms, but I use them. I use them to my benefit, to the benefit of my field. I use them in mechanical engineering. I use them for COVID-19 data analysis, and I also use them for astronomy. So I believe most of the participants in this webinar would also be engineers, mostly mechanical engineers. So you really don't need to have an understanding of uh, how an algorithm is created from the scratch. If you know, if you have an algorithm, if you know uh, the core basics of how it was built at the first place and how you can use it, that's mostly good enough. But of course, having a broader understanding of the algorithm would be beneficial, but not necessary. So this will be from a perspective of an applied person, that is me. So I hope you enjoy this. Uh, so what is regression? Regression is a pretty complex word for a very simple thing. The simple thing is finding relation between two variables. You have two variables, any kind of variables that you have, and you just want to figure out the relation between the two. What sort of relation is there? Is it a linear relation? Is it decreasing? If is the variable y, does the variable y decrease as variable x increases, or does it increase? If it increases, then what is the kind of curve it follows, and how fast or how slow is it going to increase, and things like that. So you just need to find relation between two or more variables. That's that's all. That's what regression is in its basic sense. So we have two examples over here. First, we'll talk about the left one. So there is this table that I made. On the left, you have grid point on a scale of 10. So this is not a grade point that we have at universities. This is a greed point, how greedy a profession can be, and how greedy is generally how is perceived. And on the right column, I have the profession named. Okay, so say on this greed point, we have uh, uh, a greed point of 1, and that would probably relate to the profession of social worker. This is the kind of data we have. It relates to a social worker because the social worker is mostly working for the benefit of society and not their benefit. So we can say that there is less greed involved. So um, we'll rate that as 1. Then comes the scientist, because be it India or be it anywhere else, scientists are not paid well, not enough that they should be, not even funded enough to carry out the projects. So on a greed scale of on a greed scale of 10, they would be at 2. Then we can say professors at different universities, institutes. Patange sir would relate. Then it's somewhere around 6. We can have a business person. So this is the data we have. 1, social worker; 2nd, scientist; 3, professor; 6, business person. Now we want to figure out what is happening at grade point 10. Which is the profession at grade point 10? This is what regression is. You have some data in multiple variables, in more than one variables, and now using the data that you already have, you want to predict what's going to happen further, or what's happening in between where you do not have the data, or uh, towards the start. So this is sort of the end where the curve would end, because the scale is of 10. So any guesses which profession would be at a greed scale of 10?
A politician.
A politician.
Perfect. So that's what a regression is, a politician. That's what my answer was as well. So that's what a regression is. You had a data, you tried to analyze it, and you predicted the outcome of some other data point where you didn't know what your answer, right? So everyone almost predicted so correctly that it's a politician. Okay, on the right hand scale, so this is an image I added to tell you that regression is not something new. Regression is something you have been doing since, at least since your 11th standard, because that's when we started plotting graphs. We take this experimental data, we plot these data points, and then we connect the curve, and then we say, oh, it's a linear curve. So the relation between this x-axis and y-axis, whatever this data is, we know the relation is linear, and now we'll calculate the slope of the curve, and then the intercept of the curve, and then we'll have uh, the equation of our line, or the relation that we want. So this is exactly what regression is. We have data points, we connect these data points, somehow we try to find the relation between these two variables, x and y. And once we have this relationship, once we have the mathematical equation for it, or a model for it, then we can add unknown data points. Like here, suppose you can see that there is no y value at an x value of 58 or something. We know that we have a value over there. But now, after we know this equation, all you have to do is put x equals 58 in your equation, and you'll have the y value. So this is what regression is, essentially, in the simplest form. Okay, so some other examples of regression and where we can use it. Why are you attending this session today? So we know what is regression, and now why you should know what regression is. Why anyone should know what regression is. So these are some questions that can be answered using regression once we have the right data. So do socioeconomic status and race affect educational achievement? Now, this makes a lot of sense, right? Because socioeconomic status can actually hamper the kind of education one receives. So maybe if we get the data, we can answer this question if we have the data on socioeconomic status and the race. And at the exact same time, we know the kind of educational achievement this person has, uh, uh, the person has. So we can plot this data out, or we can create a model and try to understand the relation between this. And maybe we'll get something like, yes, it does. Do education and IQ affect earnings? Now, this is a very unique question, and almost everyone would be intrigued to know the answer for this, and I am too, because do education and IQ really affect earnings? Is it just the education and your IQ that affect earning, or it's more than that? It's more than, it's also your experiences, the kind of luck, the luck factor that we'd say. Does that enter this too? Do pressure and from a physics perspective, do pressure and temperature at any point depend on the altitude from sea level? We know it does, right? So this is also a question that can be answered. We can have pressure and temperature values at different altitudes from sea level, and then we can plot that out and we can see how it varies, right? Plot it out and regress and see how what function it follows and how it varies. Do people tend to buy more expensive products during festive offers on online platforms? Now, this is again a very interesting question, because it is generally said that during this festive offers, they hike the prices and they actually sell things at a higher cost than before the sale or after the sale. So, do people tend to buy more expensive products during these times? This is also something we can get the data for, regress it and see the kind of curve it follows. Does it increase always? Does it always decrease, or it increases and decreases at different times? How does the income of a person affect the cost of the car they buy? So, is it always true that higher the salary, costlier would be their car? Would this always be true? Because I don't think it will always be true, but the data would actually be very interesting, because after some point, we can see that people tend to buy cheaper cars, even if their income is really high. And many more questions. There can be so many, like from this list, you can figure out that you can already make new questions in your domain, in your field, be it management, be it business, be it engineering, be it science, be it physics, or be it math, be it any domain where you have data, you can use regression. You will have to use regression. Now you either do it technically, or you just see what the data points follow. That is up to you, and also the complexity of the problem. So we really need regression everywhere, and everyone needs it. Everyone does it, and we do it on a regular basis, in our mind at least. But this session would be about a more technical way to do it, and a more technical way to get your answers. Um, I'll just take a break. Patange sir, can you switch off the lobby? Because I
Yes,
see,
yes. Yes, Naman, I'll
yeah,
do it. Yes.
yeah, I see that many students are in the lobby. Okay, so next up. Okay, so um, our first type of regression, or the curve that we are going to follow, is a single independent variable regression. So we have one single independent variable in this case, the simplest case, the
Naman,
case that we,
hello.
yeah,
There
yes,
is
sir.
problem that I am not the host of the meeting. So you are the host. So
Okay,
can
okay,
you just quickly do it?
this is, I try to do that. Probably have to stop my screen share. Do we know where this setting is? Is it in meeting?
Otherwise, you can go ahead. I will just keep allowing people, or I'll keep taking them inside.
Okay,
Yeah.
that should be fine. Huh. Uh, so we were at single independent variable regression. So in this case, we have just one single independent variable, that is one x and one y. So as x will vary, we'll try to see how y varies. And I tried to do a hands-on using Davis. It's a very small, easy tool to get this done. Okay. First up, the simplest one, linear regression. We have a linear equation y equals mx plus c here. So in today's talk, the terms we'll use, we know that we use this as intercepts and slope, but here we'll call m as weight. That is how x is going to be weighted. It is a constant, and it will weight x. It will weigh x basically. It can vary from anywhere to anywhere. Then we have independent variable x, that x can be anything, x can take any value. But why is a dependent variable? Y will depend on what the value of x is, what the weight m is, and what the constant c is, right? So this is how it should look like. Generally, we have these data points. Now on x-axis, it's my sleep in hours, and on y-axis, it's my grumpiness on a scale of 0 to 100. So as my sleep increases, and as I get more and more sleep, my grumpiness reduces to a particular value, and this is fairly a linear curve. It may not be for you, but yeah. So we'll see an example for this. We'll see an example for linear regression using Davis. I'll tell you how Davis works. First, I'll tell you a little about the data that we are going to use for this particular problem. Okay, so this is COVID-19 data for the Mira Bhayandar Municipal Corporation, and what you can see here, you can see the dates when this data was
Man, can you
recorded.
just zoom it? Can you just zoom it?
Yeah, sure.
Yeah.
Then we have a number of COVID-19 positive patients. On that day, how many positive patients did we record? Then how many discharges we recorded? How many deaths? Uh, Then we can of course calculate how many active patients we have from these data. That will be total number of cases, total number of positive cases minus discharge minus death. And we have total cases. So total cases is just a cumulative sum of positive patients. Cumulative discharge is just a cumulative sum of discharges, and cumulative death is just a cumulative sum of death. Okay, so this is the data. Instead of dates, I will be using this numbers 1 to whatever date we use. Okay, so for a linear regression, uh, I will take the data of total cases and total discharges, because uh, logically it should be fairly linear, right? Because the total cases and cumulative discharge, because as the number of cases would increase, the number of discharges would increase too. Because if 14 days earlier, because we had a 14-day cycle, so if 14 days earlier you had 200 patients, so you would today you will discharge more patients uh, from that 200, maybe 100, 150, if before that you had like 100 or something. So this should be fairly linear, but we can check this out if it actually is. So I'll just copy this data till the point we have this data. And now this is Davis. Uh, so right now, why do you see my screen, like why every icon on my screen is so small, is because of Davis. Because Davis right now is facing an issue. The issue is simply that on your Windows settings, uh, you generally have this scale and layout option, which is generally 150%, and uh, that is the normal way to do it. But Psi Davis doesn't work with 150%. This is a problem that I faced recently. And the workaround right now is just change it to 100% and Psi Davis works like butter. So, but it is a big platform. Many people use it. So I'm sure this issue would go away in some time. Okay. So it's a very easy, lightweight tool that one can use for many types of analysis. So if I zoom into this, I cannot zoom into this, sorry. But you can see that we can have many different types of plots, line, scatter, line to symbol. You can have vertical bars, horizontal bars. Then we have some 3D graphical options as well. We can take fast Fourier transform of data. We can convolute the data. We can deconvolute the data. This is really interesting that it can do it so easily. So there are many things that we can do here. So right now what I did is I simply pasted the data I copied from my Excel sheet, right? This is the data. I have x-axis, y-axis. Just select, what you have to do is select this data, select these columns where you have the data. Make sure that the data type is numeric if your data is numeric, because sometimes it takes as categorical or alphabetical or something like that. So make sure it's numeric and just plot it. So I'll plot a scatter plot. So I'll just plot it to know what my data kind of looks like. Yeah. So on x-axis, I had total number of cases, and on y-axis, I had the number of discharges. And we can see it's a fairly linear curve, right? When we are in an ideal scenario, this is probably more linear, but of course the real world data has noises, has errors, so this won't be linear enough. But yeah, so all I'll do here, I have to now regress it. I have to fit a linear curve because I think it is linear. So I'll right click on the plot and you get an option called analyze. Now you can just click on this analyze option and you see so many options. You can fit a linear curve, a polynomial, exponential decay, exponential growth, Boltzmann, Gaussian, Lorentzian, multipic, that is multipic Gaussian, multipic Lorentzian. We'll see an example for some of these. And you can also interpolate or uh, do a fast Fourier transform. So here we think it's a linear curve. So for a linear curve, I really do not have to do anything other than just clicking fit linear. I click on fit linear. This is my results log. So that I know what the result is. And this is my fit. This is my curve, which looks fairly good, except until the total case. So from here, you can also determine that when you can use this equation and when you cannot use this equation. We can see that at the initial points, that is till 100 total cases, it does not correlate well with discharges. And that makes sense. That logically makes sense because initially, this would be probably until 10 or 14 days because you won't have any discharge, right? No one would be discharging, but your total number of cases would be increasing. So this is what it shows. Because initially, when you start to gather the data, because this data has been gathered from the first day a COVID case was detected in this region. So initially, you wouldn't have a discharge until like 10 days or 14 days when you'll have your first discharge. So till that point, you'll only see a rise in the total number of cases. So you should not be using this before you have 100 total cases in this region, and you can do this kind of things. For here, we'll see the result log now. In the result log, you can see we have chi-square value and r-square value. R-square value generally shows you the kind of correlation there is between the two variables that I inputted, right? So here it shows a correlation of 0.987, that is 98.7%, which is a very good correlation, which is a good correlation which you can rely on. you can say that, yeah, there is a very strong correlation between these two variables, and it's mostly a linear curve. Chi-square value, this should mostly be in small integers, but that is for normalized data. This data was not normalized. So when you try to normalize this data, you'll get a chi-square value of somewhere around 1 or 0.8 or something. And you can use that as a parameter to understand how good your fit is. And chi-square basically tells you how far your predicted point is from the original one, right? So if say at 400, at x value of 400, the original y value is 300, and I get a value of somewhere around 290. So that it will calculate the deviation between these two, the 300 and 290, and this will be done for all the data points, and you'll take a sum of it, and this is what your chi-square is. And you also get the equation for your curve. So the equation is ax plus b, and this fit should give you the value for a and b, and that will give you a function. So this is a, the slope, and this is b, the intercept. So it also gives you the error on it, because, well, that is important. You will always have some error in your data. So this is it. Now you have the equation, right? Just write down this equation and input any x value and get a y value, and that's it. That's a regression for you. That's linear regression. Another thing that you would want to do here would be to add errors, because the real world data would never be error free. Mostly it won't be error free, because there are so many different kinds of error that can uh, propagate through this data. So I will add error. I don't know what the error is, right? I don't know what the error is on each of the point. So if I know what the error is for each of the point, I can add another column here, calling it an error column, and I can put the error values. But right now I'm using percentage of data. That is, I'm adding that there is a 5% error in every data point here. So I'll add these errors, and now I can fit this again, because okay, table 1, 2, yeah, that's right. Why is this not in the data? Okay, there is. Okay, so another thing that you can do here is add or remove the curves. So you have all these curves which you plotted now, but now you want to fit something else and things like that. So you can just select them. I can select all these linear fits, and I can click on this left word pointing arrow, and this would remove all this previously done things here. Let's try this again. But as I said, Scidavis is facing some issues at this point, so it may not actually do the fit for us. Yeah, it didn't. Okay, but you can do this. Once the issues are solved, you can do this easily with Scidavis. You can just add error values for all these data points, and you can do this. Okay, so this was a normal case of linear regression, where you have one independent variable, one dependent variable, and you can simply do this data fit. But of course, no one will tell you uh, um, beforehand that you have a linear varying data. You will have to look at your data and decide if it's linearly varying or if it's varying in a different manner. Now, similarly, we have a polynomial regression. Uh, so a polynomial regression, simply this is the equation ax raised to the power n plus bx raised to the power n minus 1 plus until nx plus z plus z. So you really have just one independent variable here. that is x. You do not have multiple independent variables. That is just one independent variable, but it's following a different curve. It's following a different function. And if you set if you set n to 2, you have a quadratic equation. If you set n to 3, it's a cubic equation. So you can have this kind of curves as well, and you would want to fit this. You would want to know how to regress these points too. So for that, we'll again go back to the data we had here. Now I'll try to plot. Uh, Now I'll try to plot the dates, that is the number of days, with total number of cases. Previously, I did it with cumulative discharge, which was fairly linear with total cases. But now we'll do it with we'll basically plot total number of cases with respect to the dates. So I will have uh, the dates on my x-axis, and I just want to clear this. And on y-axis, I will want there to be the total number of cases. So if you have this software installed already, you can maybe at least look at, if you do not have this data, you can at least look at the different functions that we're using here. And we can plot a scatter. Okay. Here we have our scatter plot. Now, it can be said that this is not a linear curve for sure. This is nowhere near linear regression, but we'll try to fit a linear curve and see how it is. Okay, so this is the kind of fit we get for a linear curve, which is really bad. It doesn't imitate our data at all. So now we'll go for polynomial regression, that is fit polynomial. You can you can fit this polynomial to any degree till 9, because after 9 it will be computationally very expensive. So the default value is 2, because uh, except linear, the lowest order for a polynomial is 2. And you can select the color. You can select the color in which you would want this curve to be. I would not want it to be red, because we already have a red fitted curve. So I'll make it green. And we can fit this. We can fit. So we see a very good R square value. But of course, this is not always it. You need to see your curve if it's actually explaining your data very well. So here we have the curve. It almost does imitate our data really well, but you can at one point realize that towards the end, this curve would be going more upwards. It will have a higher slope than the quadratic curve, and this should be visible from here, that if you extend this data further, so the data will actually follow this line, but your quadratic curve is going to follow this line. So when you add more data, the quadratic curve probably won't imitate it exactly the way you want. And this is the same thing towards the start as well. There is a deviation in the slope, which we see for quadratic curve and the data points. So now we'll try to fit a cubic curve, because, well, it can be cubic. So we'll fit a cubic curve. I'll give it a blue color and just fit an R square of 99.85. Fairly good. The chi square value is much lower, and we can see that yes, it does actually show that if the data increases in this slope with this slope, then your curve would also increase with the same slope. So a cubic curve here would be more suited for my data, for the data that I have, than a quadratic curve. So this data actually comes from one of my COVID-19 analysis projects, and this was published. This data and this curves were published. You can see this legend, and you can edit it. Once you double click on the legend, you get these options. You can edit the names, you can edit the colors, the fonts, and everything. You can edit the title just by double clicking on it. Even the x-axis title, y-axis title, and once you have a kind of plot you would want to publish or you would want to save for future, you can save in multiple ways. Okay, cool. So far, so good. Now let's move back to this. Okay, so we saw linear regression, we saw polynomial regression, and now getting to more difficult curves in a way. That is, there are other standard curves that maybe you would want to fit. You can see this is exponential growth. On the right, you have exponential decay. On the lower left, you have this is a Lorentzian curve, and on the right, you have a Gaussian curve. So you can you can have this different standard curves which are fairly standard in a way that most of the people use them. So these are some other options that you can try regressing if you have such a data, right? So we'll move back to our data, which is again a COVID-19 data, but from Kerala. This is a data from Kerala, and the different columns here depict date, confirmed cases, recovered, deceased, that is death. Critical, we do not have any data for critical cases. Then active cases, tested, observation, that the number of people that were under observation. This shows the number of people that were under observation. Home observation. This was okay. This was then divided in home observation and hospitalized, and then we have this numbers that just represent the dates. So we'll copy the observation data, that the number of people who were under observation, and we'll try to see how it varied, because Kerala was a very in the first wave, Kerala was a very highly variable state in a way, I can say that, because the cases, they went from 1,000, they went from 0 to 1,000 to 9 active cases and then to 10,000. So it really varied a lot in that manner, and we'll just clear this data and paste the observation, the number of people under observation. We'll close this curve. Okay, perfect. And we'll plot a scatter. Oops. Did I do it wrong? Sorry, just a second. Okay, till I do a Gaussian fitting. That's just a Gaussian fitting. If someone has any comments, questions, we can take a few. You can just, you don't have to raise your hand. You can just unmute yourself and start asking. That's fine.
Hello.
Yeah.
Yeah, so I had a doubt regarding the normalizing data thing. I don't understand that.
Okay. So right now, I'll just show. My data values are arbitrary. They do not really have a range. They are going anywhere from 1 to 777, right? So
Yes.
My algorithm, or my tool that I'm using, it doesn't know what the range for this data is. It can as well go up to 1,000 or 10,000 or anything like that, right? And
Okay.
when I calculate the chi-square values, the chi-square values that you saw that were in thousands,
Right.
that is a very bad value. chi-square of thousands is a really bad value. You cannot say that it's a good fit, but it will be bad because your data numbers are so high. You have like 500, 600, and 700. You have numbers like these. So when you calculate chi-square, it is nothing but, say, your actual value was 500, your predicted value was 400. So it is under root 500 square minus 400 square. So that will be 100 square, and an under root of that. So that will be 100. So that is a chi-square of 100. So what you do is here is you would just want to calculate, say, under root 1 divided by under root 1 square plus 5 square plus 6 square plus 8 square plus 12 square, and all of this. And you will get it from a scale to 0 to 1, right? If you do this,
Okay.
you'll get it from a scale of 0 to 1. So now when you have your data and say you have an observed value of 0.6 and your predicted value is somewhere around like 0.59 or something like that. So now if you do the math, under root 0.6 square minus 0.59 square, so that will give you a good chi-square value. That is the right chi-square value.
So basically,
Right?
you're trying to tell me that the chi-square value should be as minimum as possible.
Yes,
Is it?
yes. It should be as many. It is the deviation of the predicted value from the observed value.
Got it. Got it. Got it.
Yeah.
Thank you.
Anyone with anything else would want to ask? Okay, perfect. I can see why I had a problem there. Cool. So this is the observation data. This is the dates, and we just plot a scatter, and it looks something like this. As I told you, at one point Kerala had 1,000 active cases, and at another point it had 9 active cases. So you can predict, right, that when the number of cases were increasing, they were trying to increase the number of people under observation, under home isolation or under hospital observation or anything such. But when the number of cases started to reduce, they would reduce the observation numbers as well. They would reduce the number of people under observation. And this is normally what we would do. But this actually is a paradox, because if you keep on doing this, because of reducing the number of people under observation, you will again increase the number of active cases. And again, if the active cases increase, you will increase the number of people under observation, and this will continue. This is a cycle. So the perfect way to, try to diminish these active cases of COVID-19 would be to keep on increasing the number of people under observation, or at least constant while the number of active cases are decreasing. Follow that kind of rule. So here we definitely see that this can be a Gaussian. This can fairly be a Gaussian. Maybe not a Lorentzian, because a Lorentzian curve has it doesn't have such a steeper ending. If I would want to annotate it. So if a Gaussian curve falls like this, so a Lorentzian curve would mostly fall like this. It will fall earlier than a Gaussian. Here we can see that, yeah, it falls quite slowly. Then we can say that it is maybe a Gaussian. But after annotating, how can I? Okay, fine. That should not be a problem. Okay, perfect. So now we would want to fit this. Now I can see that there are at least 2 Gaussians, because there is a one Gaussian peak here, and then there is another Gaussian peak here, I guess. There should be one. From the data that we have, we would like predict it to be a Gaussian peak, but it may not be a Gaussian peak. Like if you move further, it may be fairly different. But from the data we have, that's what we'll get. So you have this option of fit multi-peak, because we have 2 peaks. We cannot go for a single Gaussian. So we'll have to go for a multi-peak Gaussian fitting. When you do that, it will ask you for the number of peaks. You can increase this if you have more number of Gaussians. Here we have 2. Here we think we have 2. So we'll say 2 Gaussian peaks. And now, because these are Gaussian curves, the algorithm to work quickly, it would want to know the estimate of the Gaussian peak, because of course we are humans and we are smart. We are smarter than the algorithm. So it would want a good guess from us for it to converge nicely. So you just double click wherever you think your Gaussian peak is. I double click here. So if it's green, then it's selected as a estimate, and I'll consider the other one to be here. And I have a peak. I have a fit, right? So we can see the values. The R square value is 99.5 and something. Chi-square value is way too high, and that is clearly because of the kind of data we have. It is 10 to the power 5. So if we normalize the data, we get lower values. And we get the Gaussian equation because there were 2 Gaussians. So this is a sum of 2 Gaussians. So the function is y naught plus square root 2 by pi, and you can copy this whole thing. And for each of this variable, we'll find a value here with an error, which you can of course copy with an error. And that's it. That's you have a multi-peak Gaussian curve, right? Now you can put any value of a new date value, and you can find the number of observations, the number of people that were under observation during that time. And you can find some Gaussian parameters like the center, the width, that is the full width half maximum, and the height, and things like that. So far so good. Does this all feel right to say? So this is Cy Davis. This is Cy Davis for you. A fairly good tool, which is currently undergoing some issues, but shouldn't be a major problem. Okay. I would now like to get back. So there were so now until now we've seen linear regression, we've seen polynomial regression, and we've seen regression of standard curves, which are neither linear nor polynomial. But now there can be other things like non-standard known curves, which I just forgot and closed sideways. So there can be other curves which you know the function for, which is in your field it is a known function, it is a proved function, but it is not a standard. It is not a standard equation in this tools, in this kind of tools that you have. So this is a Blackbody equation. If you remember this from high school, this is a Blackbody equation, which is in one variable. The only variable here would be the temperature, the T that you would get. Sorry, there are 2 variables, nu and T. Nu is the frequency, that will be your independent variable, and radiation, and you will get the value for T, that is temperature. You don't have the value for it, but since it is a constant for this whole curve, it will come out as a constant. So you do not need to point it out as a variable. There is only one variable, nu, and your T, which is unknown constant that you would want to know. Other constants are something you know. So even for this, Cy Davis has something. You can, while you try to analyze the curve, I would have to paste some values. Okay, perfect. So when I right click on this, click on analyze. So we have all these values, but we also have another option called fit wizard, which you can click on, and then you can define a function that is user defined. If you go on to user defined category, so these are the basic functions that are available, which you can try to fit. Then if you have a plugin, if you download plugins online from somewhere online, then you have built in. These are the functions we saw. And you can have user-defined function. So you can define your function. You can define, you can name the parameters. You can name the whole curve as Blackbody. You can add the expression, and you can try to fit. So if you know the function, but it is not a standard function, it is not available inside Davis or anywhere else, what you can simply do is you define a function inside Davis and then fit that. Side it doesn't mind that. So that is a good option, a very good option to move ahead. So now we move on to multiple dependent variables regression. That is dependence regression where we have multiple variables, not just one. At this point, I would ask if we have any questions, because we have completed one very important section of regression. We've seen linear regression, polynomial regression, regression of standard known functions, and regression of unknown functions, known functions but non-standard equations. And at this point, I would also like to change my window size to 150% because this is too small. Okay. At this point, do we have any questions? Any questions, any comments about what we have been doing? Nothing. Okay. Okay. So there are some people who are typing in chat. It would be good if you could speak, but if you're not getting proper fit curve in earlier example. Rita, do you want to say something? I don't think your question is complete.
Yes, sir. In that previous one, now which our curve was getting, that was almost fit to that required one, correct? Now, if in that case
Right.
we are not getting, again we have to change that one, correct? We have to increase the degree or something like that.
So in Gaussian, when you're working with Gaussian, one
Yeah.
place where you can actually go wrong is the estimates, because the function really relies a lot upon what you estimate. I was quite lucky that I got a good fit in my first instance. But if I give it a bad value, if I give it a bad estimate, where we clearly know there is no peak, no Gaussian peak, then it would give me a very bad fit.
Yeah, but in that case, we should go for another this one, no option then. Like previous one, we first check for linear one, then we went for
Right.
quadratic like that, correct? No, so
Yes.
in this case
Yes.
also
If
we
you
have to go for
if you say
degree.
do it 10 times, if you're
Hmm.
very convinced that it is a Gaussian, and you do it 10 times, and you're still not getting the right fit, and you can see that it varies quite a lot from a Gaussian, then you can be convinced that, oh, it's not a Gaussian. Then we should check something else.
Yeah.
It should be something else.
Okay.
In my
Yes,
case,
no. My question is, can we change in that same one, whichever we are fitting, trying to fit that one? So, can we go for steepest or something like that, or change the degree?
yes, we can. We cannot change the degree of a Gaussian because there is no degree of a Gaussian. There is a degree for
Yeah.
polynomials.
Degree means that curve
But
nature. Yeah. Yes.
yes, but you can maybe increase the number of Gaussians, or you can fit a Lorentzian,
Okay.
because Lorentzian is quite similar to Gaussian, and we may not be able to differentiate between the two just by looking at the data. So you may want to do a Lorentzian then and see.
Okay.
So in that case, you will just remove this Gaussian curve that you have from your data, the way I showed it. Add remove curve, just select that, remove, and fit a new curve.
Okay. Yeah.
Or
Thank
fit over
you.
that, and anything is fine.
Or Naman, we can go for hyperparameter tuning as well if we are dealing with machine learning. That can be also
Yeah,
an
if you're
option.
if you're dealing with machine learning, that can be the case. But in Gaussians, we do not really have. We of course have parameters, but that is mostly the peak that we can handle and the number of Gaussians that we can handle, because other thing, every
Gaussian
other thing.
actually you can deal with the width and height of the curve, but then again it will be a trial and error method. I mean, you just have to
Yeah.
repeat and
Yes,
see.
yes, yes.
Like, yeah.
Yes. So once you set the peak, you're almost setting everything. But of course, if you know the width properly, perfectly, if you know the height perfectly, you can give some commands for that as well and see. And this is more, easy to do in Python and stuff like that, when you want to play around a lot with all these values. Okay, perfect. Just one request, anyone putting out a question, please do not address me as sir. I just graduated last year, so just call me Naman. That should be good. Okay, now we move on to multiple dependent variables regression. So again, we can have linear regression in multiple variables. There can be multiple independent variables, x1, x2, x3, x4, up till xn, whatever your n is, and plus a constant z. So in this case, all your x1, x2 will be independent variables. You will only have one dependent variable, because you will always have just one dependent variable. That is a general rule. And you will have weights, a, b, all the coefficients to your independent variables would be your weights. So at this point, maybe you would like to perform linear regression on this multiple variables, and for that we'll try to use Weka now. Weka, this was developed by University of Waikato, Hamilton in New Zealand. It's a really good tool. It's a really beautiful tool that they have built for all machine learning related applications. Regression, classification, clustering, neural nets, everything. And it's well documented, and it is being used by many people. So let's see, let's first have a look at the data that we'll try to fit using this. So we have this data. Of course, I took this from some site. So what this shows is there are some startups, some 50 startups for which we have the data. We have R&D spend, that is how much that company spent on R&D, and then their admission costs, administration costs. What were the costs for administration? What were their marketing costs? Which is the state they belong to? Because state would be a good factor.
Excuse me.
Yes, yes.
Actually, we are just seeing the PPT, the linear regression PPT. I'm sorry.
Oh, okay.
I'm extremely sorry.
Not a problem. Thank you so much to tell me. But you should have. Can you see this Excel sheet? Oh, you can't.
Now we can.
Now you can. Okay.
Yeah, thank you.
Perfect. So we have this data for 50 startups in an Excel sheet. In the first column, we have R&D expenditure, how much a company has spent on R&D. Then administration costs. What are their administration costs? This is of course for US, so everything is in dollars. And we have marketing costs, and we have the state to the state that which this company belongs, and then we have the profit. Now, what you want to know from this is, how does the profit depend on these factors, on your R&D and administration or marketing? So if you know that, if you know how it how much weight is for marketing, how much weight, that is the coefficient, is for administration. So the higher the coefficient would mean that it depends more on that particular factor. So if you find that the profit is more dependent on marketing, it is say 0.78 into the marketing variable, so that would mean that you really should spend more on marketing. That's what the trend says, that the companies which have spent more on marketing have been making more profit. So this is something that we would like to know, we would want to know, and we would use Weka for this. So can you see my Weka GUI, the small box on the top left?
Yes.
Yes, it can be seen, right? Perfect. So we'll click on Explorer, where we can really explore. That's all it means. Since I have multiple applications running right now, it will be a little slow. You'll get this Weka Explorer. So you can do a lot of things here. You can classify, cluster, associate. You can even select attributes. You can have multiple ways of selecting attributes, and you can visualize the data, which is really cool. But for all of that, you have to first open a file. You have to give it a data. So I'll try to locate this data that I have. It's here. So here's the CSV. You have to change the name for the file type. It is by default it is ARF. If you have the data in ARF, that's fine, but mostly we'll have data in CSV. So we'll change it to CSV and we'll import this. Okay. Now here you can basically choose the attributes that you want to keep and want to remove from your whatever you do after this. So if you want, if you don't want state, because state is in letters, right? It is categorical, and everything else other than state is numerical. So if you want to remove state, you can just click on state and remove, and it won't be used further. You can visualize the data. It is really light, but you can see the curves. So this is how. So on x-axis we have marketing spend, and on y-axis we have state. So I would not want to have state here. I would say have profit on y-axis. So I would want to see how profit differs with marketing spend. So we see that there is some structure to this data, right? Profit varies fairly linear in some linear manner with profit, but in marketing spend, but there is some different curve followed in between here and things like that. But you can see it is a little, you can say that it's relatively a lot linear. And then you would want to see what administration looks like. Well, it's a mess. It's a complete mess because you cannot figure out anything from this. This is just a cluster of points. I cannot see anything at least. Then you can see what the R&D spend. Well, it's way too linear. It's a really good. So we can already say that if you increase your R&D spend, you will increase your profits. This can already be said from this. But you want to know how this affects overall, because you have some amount of money that you would want to put in administration, some in marketing, some in R&D. So you want to know how much in what. So all you have to do is just first just close this visualizing. Go to the classify. So for a regression, Veka doesn't have a dedicated section for that, but you can go into classifier section and you can choose a function from functions. So there is one sub file that we have here, sub file options, and if you expand that, you'll get the options that you want. You can have Gaussian processes to fit this. You can have linear regression. You can multi-level perceptron. These are different examples, different algorithms, and you can have SMO regression. SMO for regression, that is. SMO is an optimizer for SVM. So this is basically SVM, support vector machine, that we'll be talking about. So we'll select linear regression here in this case, and you can select if you want to do cross validation with this data because you have 50 rows, or you can percentage split. Now what this means, I'll make it 80 first. So what this means is you have this 50 rows, right? You have 50 rows. Now if I try to train my data on my algorithm on this data, that is say use training set, that is I use all these 50 rows to train my algorithm. If I do that, I'll get a perfect model because you're using all the training set you have, and that should really give you really good high accuracies, right? It gives me 97.49% correlation, that is similar to R square, right? But I would want to see if when I train my model, when I create this model, I would want to test my model by giving it some data for which the output is unknown, right? So what it does is it knows that the output is profit. I declared that at this stage. From here, I declared that my output is profit, and I have selected percentage split as 80%. So what it will do is it will randomly select 80% of the data. 80% would here be 40 rows. So it will take any 40 rows and it will use these 40 rows to train the model. No more than that. It will use this 40 rows, and then it will use, say, suppose the last 10 rows. If I have this last 10 rows, it will use these. It will assume that it doesn't know what the profits are for these rows, and it will only take this input data and it will predict the profit here. Okay, it will predict the profit according to the model it has built, and then it will compare the profit that the model gives and the profit that is actual, because we actually know what the profit is, right? So this way you can test your model. This is a more robust way of doing anything related to classification or regression using these algorithms. No one knows in this whole world that what is a good ratio for the split. It can be anything from 60% to 90%. And this is something that we have argued upon in our paper that was published in ASME. But I generally prefer 80%, but it also depends on the number of rows I have in my data. Right now I have 50 rows that are limited number of rows. So I would want more training data when compared to test data. So
Naman, I would like to add one point.
yes, sir.
So the thing is, Naman last time he used the support vector machine in Veka. So in Veka, it is not normal support vector machine. However, it is optimized support vector machine. So the optimizer function is sequential minimal optimization. What he said is SMO is
Yes.
sequential minimal optimization. That function is driven support vector machine it is. So if you are dealing with Veka, there is no simple Veka SVM available. So you have to deal with Matlab or Python for simple SVM.
Yes.
However, yes. So however, in Veka you have it is optimized SVM, that too with sequential minimal optimization algorithm.
So yeah, why do we need optimizers is because SVM is a fairly complicated algorithm and it needs kernels. So there are different kernels that you need. We'll discuss about this. So there are different kernels that it needs, and it's fairly complicated. So to optimize it, to take less time to do your job, it needs optimizers. So there are many optimizers out there, and SMO is one of the most used and most famous ones, and it is a robust method. Okay, so here we have a percentage split of 80%, and we'll now start this fitting, and we have 99.09% of correlation coefficient, and you can see the equation. The equation is profit is equal to 0.7966 into R&D spend plus 0.0299 into marketing spend plus a constant. And this makes sense, right? Because R&D was something that had a very good linear relationship with profit, and we can see that it has been weighted nicely, 0.796. Marketing spend didn't have a great correlation, but still good enough that it could be weighed at 0.0299, that is almost 0.03. And we saw that administration costs, they have nothing to do with the profit whatsoever. They really depend on the company, and you can reason that if you are doing this project. So it is not a variable that your profit would depend on. So you would not want to think about how much you should give into administration to get a good profit. So we have a constant number here, and so this is our equation. This is our equation. This is the fit. Veka, the only thing I probably don't like about Veka is it is less intuitive in a sense that you cannot really generate very nice uh, uh, graphs that you can play with, that you can use to understand how your predicted values differ from your observed values and so on and so forth. But I think the objective behind building Veka was to have have a tool that is lightweight, which is not computationally expensive, and which doesn't take a lot of your RAM as well. So that way it does a really good job. So what we did again, for you to use Veka, just click on Veka Explorer, open file, choose some file, and then you have all these attributes. And once you have all these attributes you listed, you can visualize your data. You can click on any of these boxes and you can start visualizing your data. Once you have an idea of your data, because it is always important to know what your data is before you do anything with it, you can just go on to classify. If you want to regress, most of the options are available in functions, and there are some available in trees. There are particular with trees. So you can do regression this way using Veka. So this is Veka for you. You can also do cross validation, which I would not want to go into right now, because cross validation, while it is important, it is more important for classification and maybe for a further talk. You can work around with percentage split. That is something we've discussed now. Okay. Good enough. We would at this point now like to go back to here. Okay, I'll close Veka. I don't want to be an issue. Okay, we'll be using Veka again during this session. So if you have any particular doubt right now, any urgent doubt, you can ask, or we can move ahead.
Well, good evening, Naman.
Yes, yes. Good evening.
Just now you said something about the graphical representation. You said that the Veka is not good for, you don't prefer
Yes.
because it doesn't show you the graphs and all about the predictions. So what you'll suggest for the graphs and all?
Yeah, so the next two tools that we'll be using for this session would be Python and Matlab. And Matlab,
Okay.
we know, is a very heavy software, which
Yes.
you wouldn't want to use if you are constrained with computational power. But otherwise, it is a very beautiful tool, right? It will show you multiple graphs in colors, and you would love it. So we'll move to Matlab in some time. So this was linear regression in multiple variables, multiple independent variables. Now we'll move on to something that is, now again, this is multiple variables, but this is a function that is non-standard, that is not linear, right? This is not a linear function. This is a gray body function that I use, that every astronomer uses a lot, and so do I. This is nothing but a modified Blackbody equation. If you remember the Blackbody equation we saw here. So Blackbody equation is basically 2 nu square by c square into h nu upon e to the power h nu by kt minus 1. Oh, everything here, most of things are constant except for nu, and temperature is something we would always want to know if we have the data, right? So here we astronomers have modified it a little because the stars that are forming, that are in the process of forming, are not really black bodies. They are gray bodies. They are modified black bodies. So you can see this. There is this term we have, which is an added term to this equation, which has a physical representation. We also have omega added, and rest looks quite similar, right? So this introduces two new variables to this equation. One is omega and the other is tau naught that we have here. Beta is constant. Beta is something I provide the program with. So tau naught and omega, these are two new variables that we have, and nu was always a variable, the frequency. That was a variable, and the output is a flux, that is brightness. So you have three variables, multiple constants, and one dependent variable, that is flux. And now you would want to fit this. You know what the function is very well, as well as this. Now you want to fit this. Now we'll use a new tool, Python, the third tool of the day. We'll use Python to fit this, to replace this. I've already written a code for this, and the data I will be using for this is my own data and is unpublished data that I'm working on right now. Yeah, so if you're new to Python, if you've never used Python, I would recommend you to download Anaconda. That is the best way to access Python. I guess it is a bit heavy in some sense, but it is still the best way if you are new to Python, if you do not really have a lot of experience on it. I still use Anaconda. I find it the best way. Just launch a Jupyter notebook or anywhere else that you've written your code in. I'll launch a Jupyter notebook. And here I have my Python script, final gray body. I'll just open the script and I'll tell you what my, you can see this Python script, right? You can see my Jupyter notebook.
Yes, we can.
Yes,
Okay.
it's visible.
Okay. So the first part of this script would be to import the necessary variables and tools like NumPy, SciPy Optimize, and LMFeed. That is what I use. Now this is my input data. This is my x-axis data basically. This is frequency in gigahertz, and then this is flux. This is the y-axis data, flux, the output, the dependent variable, and then these are the errors in my output, in my flux, because in real life when we are dealing with astronomy particularly, we can never have anything with confidence, with 100% confidence. The confidence will vary according to the instrument and many more factors. So I will run this. So I will run this. Then I would define some conversion factors because I would want the way this formula works is not in flux in Genskis that I have. The flux is in Genskis right now, but I would want it in ergs per centimeter square plus second plus per hertz. So this is just me defining some conversion factors. Somehow, okay. Then I will define omega low. Okay, just I will just run from here in this case. Then we apply this unit conversions. That is, I get my frequency in hertz, fluxes in that long unit. I define some constants, S, H, C, K. We all know these constants. And these are a few functions, which you really don't need to get into because I just use this to plot a graph. This is a function which is important. I'm here, I'm not only fitting just one gray body, I'm actually fitting two gray bodies. So what I'm doing here is I'm defining, first I'm defining this one single gray body. I'm defining the output of this second gray body. And then I'm adding both of this, which would be the output of my function here. Okay. So what I'm doing is I'm just defining this function. I'm taking all these values from the main script that I have. These are all the values I will need, the estimates and everything. And I will use them here and I will calculate my output. That is flux. Because what the algorithm is going to compare. So how the way this algorithm works, it is basically least squares. So it will try to reduce the value of chi-square because we need the lowest chi-square value, right? So while doing this, it needs to compare the two values, the observed flux, that is the actual flux, and the flux that my algorithm gives me. And that way it will keep on comparing this and calculating chi-square and keep on reducing it. So here my output is basically flux. My output is flux for these particular variables, whatever the values this function gives it, right? So I'll run this. Here I've defined my model. That is, it is the Griffith model. Just print some things just because so I thought I know that how things are working. I give weights. Weights are 1 by error. So the data that has lowest error, I would want to weight it more, right? So it is inverse relation. So weights equals 1 by error. And then I add all these variables and I give them some value. This is my initial value. And I say that it can go from a minimum to minimum value of 1 to maximum value of 5. But at the same time, I say that it cannot vary, which means the value will be 1. It won't change. You need to vary this to, when you're playing with such kind of algorithms, because now you have 6 variables, 3 for one gray body, 3 for another gray body. Then I give v reference, and where you want the variable to vary, just don't give this variable command because by default it is true. So it will vary. And now here, this is where you will finally call the fit, gmodel.fit, and you give the flux, the parameters, and then frequency. Then I give, this is the number of iterations. You can just set it to any random big value, and weights. You want to give weights. And these are just some command lines for plotting my output. So this is where it will go. It will take some set of values for these variables. It will take these values. It will go to the function. It will give values to this function. Then this output will be calculated. Output is flux, and this output will be compared with the original flux, the actual flux, and they'll see how good it is. If it's not good, it will do this again with other set of values, and this will keep doing. And I'll just run this, and I get a nice looking fit. These are 2 gray bodies to my data. I know because we know from experience that we need 2 gray bodies to fit such data. We get 2 temperatures. One is 181 Kelvin and the other is 30 Kelvin. So the 30 Kelvin is actually the temperature of this star that it's forming. The temperature of this protostar. And 181 is the temperature of the gas around it, the cloud, that is ambient cloud that is around it. So we get these temperature values, we get a value to this tau naught, which is the optical density. That is something in astronomy, important in astronomy. And from here, now I can do more things because I have the value for tau naught and temperature. I can calculate what the NH2 is. NH2 is how much H2 do we see, basically, something that is important. And this is something more familiar. I'm calculating the mass of the star, mass of the protostar. This is data from a star that has not formed yet. It is in the early stages of its formation because I'm studying star formation. So I will calculate the mass of this protostar. I know the distance to this protostar, and I get something like 9.7 through solar masses. So 9.73 times the mass of the sun. So we know this is a relatively massive protostar. Because the low mass stars, we generally find low mass stars which are around 1 solar masses. So this is which is what makes it interesting. So this is something you can do for if you know the function for your thing, and you can just define the function and give the parameters and use the fit. You can have the fit. You can play around it. I played around it for like 3 hours to get the perfect fit, which is scientifically plausible, and that's it. So does anyone have any doubt over here? Because this is the only thing we are going to do in Python. This is how you can do anything in Python. Any doubts? We're already running short on time. So if you have a quick doubt, we can take that. Okay, perfect. Yes. So back to our presentation. So this was something we did for when we have multiple dependent variables, multiple independent variables, and if the function is linear or some other function that we know. So you can use Weka, you can use Python. Now we're only left with Matlab that we'll jump onto. But now what if we do not know the function? This of course assumed that I knew this function, that I knew this complicated function. So I could write a function for that in Python and then fit it. But what if I do not know the function? Because this is plausibly what the case would be in many times, right? If you're doing something cutting edge, if you're in some domain where it is not already known, if you're trying to know, so what if you do not know the function? So there are many algorithms that can be used. Srinath, can you just mute yourself? Sorry.
Okay, sorry.
Yeah, no problem. Okay, so there are many algorithms. So this is the part where we come down to machine learning algorithms for regression, right? The last part of our day today. So it starts. So there are many different algorithms that are available. Okay, there are regression. There are decision trees, random forests, SVMs, Gaussian processes. So many algorithms that are available out there. I'll talk about two of the most famous and most used and most robust algorithms. One is decision tree, random forest. Both are quite similar, and the other is SVM, support vector machine. So we'll quickly jump onto this. We won't get into math of any of it. There's a good enough math to understand all of this. But so the first algorithm is decision tree. Here we have the data, tabulated data. Okay, our target, that is our output, y-axis is the number of hours played. We want to find how many number of hours a student or child plays, and our input parameters are outlook. Is it rainy, sunny, overcast, or anything like that. Then we have the temperature, humidity, and windy, if it's windy or not, like all the conditions. So if you can figure out from these conditions that how many number of hours is a student going to play. So what it does is it shortens this problem in small number of pieces. It will go and first find the relation between outlook and temperature. If it's rainy, then does the output depend on temperature for the outlook of rainy? If it does, it will have a parameter, and then it will see if after temperature humidity matters for the hours played, and it will cut short it to number of pieces, number of pieces, and it will create this decision tree. So now here you can see first you have the outlook. So now I give a new input. Okay, the new input is that the outlook is rainy. Okay, so we have rainy, we go into rainy. Then from our decision tree, we know the next thing we need to know is temperature. It depends on temperature. So I'll try to set the temperature. So I say, suppose it's cool. The temperature is cool. So from here, it will go to, if it's cool, then it will give me an output of 38. So it will be 38 hours played. And if you go to the data, if you find such a scenario where it was rainy and temperature was cool, so here we have rainy. So we have only one instance where it's rainy and cool at the same time. This is the instance. So it's rainy, cool, and the number of hours played is 38. So this was a unique case where there was only one instance to get the value from. So it just outputted that value because for the algorithm, it only had one data point to know what happens when it's rainy and cool. So it will say, oh, it's always 38. But when you input more data, this will change, right? So this is how decision trees work. Decision trees builds regression models in the form of a tree structure. The structure I showed you right now, it breaks down a data set into smaller and smaller subsets, while at the same time an associated decision tree is incrementally developed. While it is cutting this problem into short, you have this decision tree that is growing, a decision tree that is a decision node. So the first point that you have in a decision tree is called a node. It has two branches, so those are called branches. The way we have in algorithms, and then you have leaf node, that is the final output, which will have no further branches, and which will represent your target, whatever the output is. And decision trees, the one thing that they are really good at is they can handle both categorical and numerical data. It's not necessary that you need to have only numerical data. It can be categorical. The way you had here, if it's sunny, if it's outlook, then it can be sunny, overcast, or rainy. So this is categorical data. That is, there are three categories that it can go into. They are not numerical. These are not numerical, but your output is numerical. So it can have a set of categorical and numerical data. And then we have random forest. So what happens in a random forest? It's a very easy algorithm to understand. Random forest will create hundreds of these trees. Okay, what is a forest? It is hundreds of trees. So that's why it's called a random forest. So it will create hundreds of trees with so each tree will be like this. Each tree will give you an output. So in this case, when it was rainy and cool, this gave us 38, and it will mostly give us 38. But say it creates 100 trees, and we'll have 99 other outputs. So this was 38 here, then we have 37, 39, 38.5, 37.5, and values like that. So we have one value from each tree, one value from each tree from a random forest. So if we have 100 trees in a forest, so what will happen is we'll have 100 outputs, and the final output will mostly be an average of this output. It will average out these 100 values and give you a single output, right? So this makes logical sense, right? Because this will make it more robust. If your output is say 38 50 times, so your output of 38 dominates, and you can robustly say that this is robustly say that this is 38, because you've tried the other values. You have tried the algorithm in a way that it can try different values. So this is what random forest does. It creates multiple trees, many trees, and averages the output of each of the tree, just to make things more robust. So we'll try to see an example of random tree and random forest. So random forest is something that is not available in Matlab. It is available in Veka. There is something available in Matlab called bagged trees, which is just a lower version of, just a different version of random forest in a way. It's not exactly random forest though, but it is an ensemble method. Ensemble is when you're creating this multiple types of. So again, we open the file, we find our CSV file that we want to use. I'll try to show this, what this data is, what this data tells you. So this is a data which for which the output is the house value. What is the house value? And then we have some parameters on which this house value can differ. So we have longitude, latitude, then we have housing median age, like what is the median age of people living in that house, the number of rooms, total number of rooms, total number of bedrooms. We have population, we have households, how many households, and then we have income, which should make sense, and we know if it's ocean proximity, if it's near to the ocean or far from the ocean, that may differ its value. So this is one categorical data that we have here, and all other data is numerical. Okay, so we have input this data. We'll leave it as it is. We won't remove any rows. You can do that if you want at some point, but not now. We'll do a percentage split. And now why are we using random forest is because now you can see that these are the kind of data where a decision tree would make sense, right? You can get into the total number of bedrooms, and then you can see, okay, for these number of bedrooms, what is the median income of this household? What is the median income? And then you can go and try to find the house value. So random decision tree in this case would make sense to try out, but it is definitely worth a try. So we'll try to fit a random tree first. Random tree is just a decision tree, and the output here it's selected as ocean proximity. It will always be selected as the last column. Okay, so you want to change this as median house value because that is what your output is, and you can. Okay, so you have a correlation coefficient of 85%, which is fairly good for this kind of data, which may not be very well correlated. So we know there is some correlation, and this is the decision tree. Now this is a huge tree that you may not want to have a look at because, well, it's fairly big because we have many number of rows, many number of columns, so many parameters that it depends on. But this is a horizontal decision tree. So just an example from here would be, it will first check for the latitude. If the latitude is greater than equal to 37.59, it will check for the longitude. If the longitude is less than minus 122.41, it will again check the latitude if it's greater than or less than minus 122.45. If it's less than, if it's greater than equal to minus 122.41, it will output a value of 420, 300. But if there is a longitude is less than minus 122.45, it will output a value of 417,600, and longitude it will output a value of 324,700. And of course, there were previous variables towards the top that were evaluated before getting to longitude. So median income, so latitude was the first dependent on this. In this case, if it's less than 37.72, this tree will be followed. But if it's greater than, so there will be at some point, this would be different. We'll find some point where the latitude will be greater than 37 point, that number. Well, it's hard to find. Let me know if you find. Yeah, so this is the point where we have the other branch. Where did it go? Just found it. Oh, okay. So there is at some point. This is a huge tree. So fairly good job done by decision tree, 85%. And this is the tree. This is the conditions on the basis of which you're performing your regression. Now you have any new set of inputs, just get into this decision tree and input all these variables and you'll have your output. Of course, you would not want to do it on paper by yourself. You would just want to output this model and save this model. So which is something you can do, and save this model and work on it later. Now we'll try random forest. Just select random forest. These are there are hyperparameters which I am not varying right now, which I'm keeping as constant, but you can vary. And start random forest. Random forest will take relatively more time to build because it is building 100 trees, and then it is always taking output from 100 trees, and okay. So we get an accuracy of 92%. So that is something we know about random forest. It gives a better accuracy most of the times. And for this, of course, you will not get a decision tree plotted because you would not want to see 100 trees on your Veka screen. Already one tree was so big, so you would not want to see 100 trees. So you have 92% of correlation coefficient, which is better than decision tree. Well, this is how random forest works. This is random tree and random forest. Now I'll be opening Matlab, the final tool that we haven't used yet, and I'll do the same things in Matlab. Till then, if you have any questions, you can ask while I do this. Any questions, comments? Please unmute and ask. Any doubts, questions, comments, something that you couldn't understand, you would want me to repeat or anything like that?
Hello.
Yes.
Yeah, Naman. Good evening. My question is, as that last column in the Excel sheet CSV that we have done, so that is taken
Yes.
as taken for the classification, right? So do we
Uh,
need to select it somewhere?
Sorry for the class. What did you mean by classification?
Did you get me? See, we do the classification and regression.
Right.
Okay. Now for classification or regression, whatever,
Hmm.
is it like that the last row is compulsory, last column of the data sheet is compulsory taken as a for the classification?
No. So the last column is always taken as output, be it
Output.
regression or classification. If when you do
Right. So
classification, so it will be taken as classes, different classes.
yeah, right. So by default, it will take the last column, right? So we
Yes.
did not give somewhere that this is the column from where you have to take the classes.
Right.
By default, it
You
will
don't
take,
need to
right?
do that. Yeah.
Okay, okay, okay. Thank you.
This is something they have said. So, and generally, even we, sort of try to manage our data in such a way that on the last column we have our output. That's a more intuitive way. But of course, this time I didn't have my last column as the output. I had my second last column as the output, but it took last column. So I just changed that to second last column, and it's fairly easy to do that.
Okay,
Even
okay,
when
okay.
I
Now,
work with Matlab, I'll show you how we can do this in Matlab. Even Matlab will ask you to select what your output is, and it will by default take the last column.
Naman, can you hear
no,
me?
what?
Yes, yes, sir.
Hello. Okay, so I would like to address sir's doubt. Actually, in Weka, uh, the automatically last column will be selected as the target classes or target labels. So for classification in Weka, automatically if your last column refers to the class or target values or labels, then automatically it will be selected in Weka. But then again, you have to ensure that it has been selected in other softwares, or there is an option to declare the last column as your target or labels, and accordingly the classification is done. So Naman, in Weka, you can show them that
Uh,
when you go to select the classifier, that time there will be one drop down option, and
yes,
in
yes.
that
I
drop
showed
down
that.
section you will be able to see the condition which has been already selected.
Yeah. We'll probably
I,
see Matlab for a while because we do not have a lot of time. But you can see that. You can see the output. There is one drop down column, and you can easily select that. Just for now, we'll start with Matlab, and I'll show you how this happens in Matlab. However, Matlab is much better when it comes to computation. It may even select the second last column. So it will find what the correlations are, and it will see, oh, this is what everything correlates to. So it may select my second last column as the output. So so what I did is I opened my Matlab. I had an application inside Matlab, which is a regression learner, which you can easily install from Matlab, and just open that. I'm starting a new session. So you can start a new session either from Workspace if you have some data on Workspace, or you can start from a file. So I'm starting from a CSV file, and now you will have an import tool where you can select how do you want to import your data, because you may not always have a very good looking data. You may have data that is uh, at some columns, some cells may not have a value, may not have a correct, may not have a value, simply NA, and things like that. How you want to handle that, and uh, if it's comma delimited, if your file is comma delimited or anything else. So here I know my file. It's fairly good. I do not need to do anything here. I'll just import this file. I'll import all these columns. Okay. So now, while I've imported my data, the next option would be to select exactly what the question was right now. I would want to select my target and my predictors. What do I want as predictors? If I want to remove some, and the kind of validation that I would want to perform. So here, Matlab has automatically taken my response as median house value. It didn't take my last column because Matlab that way is very smart. It would find the correlations and then select the output. So it has selected my output. Now I can, if I want, remove some of the predictors from here, but I really do not want to do that right now. And now I can select the kind of validation. We can do cross validation. We can do holdout. This is the same thing we did there. I would make it 20. So this would mean 80% of the data is using to train the model and 20% to validate, that is test the model, the thing I explained there. And I can start my session. So once I start this session, now first thing that I can do here is look at my data. Look at how it varies with okay. Am I audible now? And is my screen visible?
Yes, sir.
Yes. Okay, perfect. So this is where you can see what your curve looks like according to different predictors. So on the y-axis, I will always have the median house value. That is my output. And on x-axis, I can vary this thing. So if I say select the median income, which I think would be highly correlated. So it is indeed highly correlated. You can see that is almost a straight line with a lot of deviation, of course, but it is sort of increasing. It is always increasing and getting broadened out. So on x-axis, I have median income, and you would want to look at your data. Ocean proximity, how it varies with the ocean proximity. So because my ocean proximity, that data is basically categorical, so it won't have data points, but you would see. So inland has if the house is inland, the house value would be the least, and this is you can see how this varies. Quite nice, and you can see how it varies with total number of rooms. Again, increasing, but maybe not so much, not so well correlated. Then you would want to see at total bedrooms, then median age, how it varies. It has nothing to do, almost nothing to do with median age. Population, mostly nothing to do here as well. Okay, so now what you can do is simply select the model or algorithm that you want to work with and just give it a shot, right? So first we'll say try find tree. So there are different type of trees available in regression, available in Matlab. You can select find tree, medium tree, coarse tree. What depends is or differs is the number of leaves that you have. The number of leaves for coarse tree is minimum 36. For find tree, it's minimum for 4. So, and you also have an option called all trees, where if I select all trees, it will try to it will try to regress using all trees one by one if you want to do all the trees. So I'll go with find tree and I'll train. Just select on train. It will take some time. You can do some feature selection as well. Maybe that is something we can leave for the next session. Whenever we have that, you can select your features because some features are really bad. You don't want to use them. So you get a correlation of 70%. Quite good, but not the best. You know that there is some correlation, and tree can do it. You maybe you want to try coarse tree now. You select coarse tree and train it. And then you get an accuracy of 73%. We would expect coarse tree to work better, right? Because we know that there are many numbers of leaves in this case. So 73% is what we get. And then we can go for boosted trees and back trees. Back trees is very similar to random forest, but it differs a little from it. But it is the best replica of random forest in Matlab. and this is, so you can find the details here. The correlation was 78%, right? And now you can also, do something like you can plot the errors. You can try and plot the errors. So if I click on errors, but because we have so many data points, it's almost impossible to realize how big these error lines are. So we have this another plot that we can do is predicted versus actual values of the income. Now, ideally, in the most ideal scenario, you would want your data points to follow this black line, right? Because you would want your observations and the predictions should be to be the same. It should be a y equals x line. But that is never going to happen. That is never going to be the case. But you can try to determine some things from this, right? So we can say that for this region, for this initial region, for a low household value, this is quite collimated. The predictions are quite nice. There's not much variation. For the highest values, it varies. For particularly at the highest value, it just doesn't correlate well. And here it gets broadened. It gets in the central position. It gets a little broadened, and you can now use this data and understand more. You can try to change the kind of hyperparameters for your model, and you can vary. You can do things like that. So this is quite nice to see this graphs. You can also see residuals. That residuals are again the difference between your observed value and predicted value. So if my observed value and predicted value are the same, then my residual is 0, right? Because residual is nothing but the difference between my observed and predicted value. So ideally you would want everything to be 0, but you will not always have 0. So this is also something you can have a look at. And that's it. That's regression using Matlab. It's very intuitive and user friendly in a way. So this was it for decision trees and random forest. Now the next algorithm that we would want to look at quickly is support vector machine. So support vector machine was ideally initially made for classification. It was never made for regression, and many people still do not know that SVM can be used for regression and not just for classification. So I'll start with how it is used for classification, and then we'll come to regression. So here you have two sets of data. What is classification? Suppose you have dark chocolate and normal chocolate. Now you would want to classify these two. If we have some input parameters, say the company name, the chocolate name, and so on, you would, in the end, you would want to say if this is a dark chocolate or if this is a normal chocolate. So suppose this is dark chocolate, this is normal chocolate, and you have this graph, you have this variation. Now you would want to use support vector machine to classify this. Okay, so what this support vector machine does is it first creates a hyperplane. Okay, it will create this line that divides it into two classes, that divides your data into two classes. It will try to make the best possible line that will divide it in two classes. And once it does that, your job is done, right? Anything below the line would be normal chocolate. Anything above the line that lies above the line in your graph would be dark chocolate. But the problems are never this simple. If you have something like this, now you cannot create a straight line, right? You can simply not create a straight line that would differ, that would nicely classify this data. So what this will do is support vector machine will go into a higher dimension. It will look at this data into a higher dimension. So this was a two-dimensional data. Now we add the z-axis and we get into this three-dimensional zone to look at this data. And here we can see that we can create a line, we can create a plane between in the z-axis between the blue and the red data, that is the dark chocolate and the normal chocolate. So it goes into this higher dimension and it creates a plane, because in some dimension you will definitely be able to create one such plane that will easily differentiate between your classes. So it will go into this higher dimension it will create a plane, and then when you come to the lower dimension, you will have a circle over here. So this is what you wanted. Now this can easy, if it's inside the circle, it's a normal chocolate. If it's outside the circle, it's dark chocolate. So this is what SVM does, and for classification. But this is for classification. Now what happens for a regression is, you have a set of data points. It creates two decision boundaries. That is one above which we do not have any data and one below which we do not have any data. So it will create these decision boundaries. And for these data points, it will go into higher dimension and it will try to get a plane on which most of these points would lie. Here, what we were trying to do is, we were trying to find a plane that would differentiate the two data. That above that plane, there would be one class, below that, that would be one class. But here in regression, we are trying to find a plane that would pass through most of the points. And when you really have such a plane, when you get it in the lower dimension, you will have that curve that would fit your data points. So this is really what SVM does. It's a really strong algorithm in a sense that it can always go into higher dimension and solve your problem, how irrespective of how complicated the problem is. But it will, as it goes into higher dimensions, it will be computationally very expensive, and you would need a lot of time to do that. So we'll do something like this for one of the data sets that I have. So this is a huge data set in a way. So this is again something where my prediction is the sale price of this house, and there are now around 59 independent parameters that we would want to use. Now, of course, this is very difficult to get into. There are numericals, there are numeral values, and then there are categorical values, right? Now I would want to use this. One thing you can do here is maybe if you want, you can edit the way you work with non-values, that is non-defined values, because you would definitely not want not defined values in here. So I would exclude rows with empty cells or unimported cells. That's fine. That's the same. So I would just exclude the row which has non-values, non-value in any. So you would really want, when your data is so large, you cannot do this by hand. So you would want to do this automatically by algorithms. And I would import this selection. Matlab generally runs faster, but since I have been running quite a few things and I have a virtual machine, so my laptop really doesn't help me work faster. We know that ID doesn't have anything to do with the house value because ID is just number 1, 2, 3, 4, 5, 6, 7, 8, just ID which is given. So I remove this. So I would just unselect it. My response is sale price, and that is cool. I will do holdout validation. I will make it 20, which is my favorite number, and start the session. And now because as I said, SVM is quite computationally expensive and even our data set is quite large. It can take some time to, again, you can here play with your data, play with the data that you have. You can see how your house resale value depends on the different factors. Say, suppose we compare it to sale type. So we can see there is some variation, but not a lot of variation because there is this line which passes through almost all the categories. So maybe not the best predictor, but we have so many predictors. And this is where you would maybe want to restrict your number of predictors. I wouldn't do it here, but I can just show. So because I have 69 features, I would enable PCA. And there is one way you can do this is specify number of components. You can restrict it by the number of components. There are 69. I would say I only want 30 components. Please use only the best 30 components. So it will use only the best 30 components. But I don't want to do it here. So then we have SVM options. There are so many SVM options: linear SVM, quadratic, cubic, fine Gaussian, medium Gaussian, coarse Gaussian. All the SVMs, this will just do all the Gaussians one by one. And optimizable SVM. Optimizable is it will tune the hyperparameters in a way that you get a better output. So what this linear, quadratic, and cubic SVM all this mean is these are the kernels that will be used to get into the higher dimension. Will it be linear or quadratic also? So you can just select this linear SVM and train your data. So of course it is training as well as testing your data, and you should have your result in some time. We have a result. The correlation is 91%, which is quite good for the kind of data we have. And now you can also see all 69 features were given to be used, and I would predicted versus actual. So this is how it looked for the predicted versus actual, and we also have for the test results. So this was for validation results. That should be the same because it doesn't show what happens with the train data. So this is my test data. Okay, this is what I get for. So it's fairly good, doing a really good job with predictions. And response plot, I would get to be okay. So this is the response plot. If you want to see the errors, you can plot these errors and then maybe zoom into the graph and see. So the blue circle is the true value, the yellow is the predicted value. So this is the difference between these 2 points. It was predicted, and you won't see it for all the data because we only tested it on 20% of the data. The other 80% was used to train the data. So this is 20% of the data, and we are seeing the errors on it, right? So this is SVM. You can maybe I would want to show the optimizable SVM. I have set it to 30 iterations. You can iterate it. You can maybe have 100 iterations, 2000 iterations, any number you want. Or you can set, you can give it some time, like run for 1 hour, run for 1 day, and you can set the length of the optimization that way. I have set it to 30 iterations, and we'll see what we get. So it will just change the tune the hyperparameters. And because this is a time-taking process, we can take some doubts while this is happening. I will show you what plot we see. We have already overshoot the time that we had, but this is the last thing. This is the last thing we are discussing today. We have today to discuss. So any doubts, any comments till now? Okay, so this is the mean standard error, mean squared error, sorry. This is the mean squared error. And what you're doing while optimization is you are trying to reduce this error, because the more you try to reduce the error, the better will your correlation get, or the better will your accuracy be. So this plot just shows you how your mean squared error varies with the iterations, with the number of iterations. And you would just want it to go down and down to the bottom. But let's see what happens. And you can see the hyperparameters that are being used. So the kernel function right now is linear. The data is standardized. Standardized data is similar to normalizing the data. So Matlab does it for you, which is nice. Okay, so while this works, this is really a huge data, and SVM is quite complicated, so it will take some time. So we can have some doubts till then. Anyone would want to ask anything or comment anything?
Where can we learn about the maths behind this hyperplanes and everything?
Oh, yes. So there are many research papers, because SVM was first introduced by a research paper. So you can first go to that research paper, and then you can see the research papers for SMO, the sequential minimal optimizer, which is an optimizer. This is Bayesian optimization, the kind of optimization that is happening right now. So you can learn about Bayesian optimization. And the hyperparameters are, of course, mentioned in the initial paper itself about SVM and any other paper that is published using SVM. Even the paper we published, we added some information on the kind of hyperparameters and the equations and the mathematical details of these models. So there's a lot available on this, and research papers would be the best way out.
Okay, thank you.
Yeah. Anything else that anyone would like to ask, comment? It's fine if your doubt is not particularly related to what is happening right now. You can just ask anything, any of your doubt that you had before.
Yeah, Naman, sorry to say, answer me only if you have time, no problem. What I was doing
Yes.
2 days back, I tried with which are already available in Vika, and that I was trying to
Okay.
do the classification. So I was successful with that.
Right.
But then when
Okay.
I had result analysis of my class of the subjects,
Pradyumna,
in
somehow
the last
I
column
cannot
I
hear
have
you
put the
properly. Your voice is breaking a lot.
okay.
Is it just for me
Yeah,
or
yeah.
is it happening with others as well?
Is it clear now?
Yeah, it's much better now.
Hello?
Yes, it's much better.
Yeah. Yeah. So 2-3 days back, I was trying
Yes.
with some data set which are inbuilt in the Vika, and
Okay.
with those data set, I was able to classify properly. But then what I did, I tried with the result analysis sheet of my students. So their third year results and of different subjects. And in the last column, I put their grades, why like they are classes, like they are in higher second class, first class, distinction,
Okay.
depending on their
Perfect.
grades. But then I was not able to do the classification with that data set. When I took it, I was not able to understand what it was doing, and I was not able to get the proper output. So do you have any such data set, and can you show with that? But only if you the time permits, sir. No problem if you cannot ask.
I don't have any data set that is similar to this, but I would still expect that this should be very well classified because your end column basically depend on the marks they have got, and they would vary. Like say if a student has higher marks, and if you have one column of marks, and your output is the class, higher second class or whatever, so that should be really well classified. You shouldn't have any problem classifying that. Which other classifiers did you use for that thing?
J48 I was using.
Oh, J48. Okay.
Yeah.
Maybe not the best classifier to do that. You can
Okay.
try decision tree, because I think decision tree should really do your job really good. Because if you know, it can set that if the marks are less than 30, then this is the lowest class. If the marks are between 30-45, this should be the class. So decision tree should be a good one for your dataset. So you should really work out with more
Naman, I would like to add some points.
models. Yes, sir, please.
So the thing is, the very first thing is you should select the option. There are 3-4 options available in Weka for classification. There is option of training, there is option of testing, there is option of splitting, and there is option of cross validation. So if you choose the option of training, then whichever data you have supplied, that will be trained, and according to the same data, the testing or validation will be done and the result will be plotted. So now what you have to do is the data which you have trained already using your original data can be trained using testing option first, and then you have to supply test data. There is an option supply test data. So when you supply test data, separate data which you have taken from students, then it will be able to classify, because in Weka we have that only one option where you can give two data set. One will be training data set and another one will be test data set. So you can supply two data sets separately. And the conditions for that particular mode is that the classes which you have used for training must be they must be same in the test data set as well. So if you have trained for 5 classes, then you must give the same 5 classes and their different characteristics or different data distribution in the test data. If these conditions are satisfied, then you will be able to do it in the Weka. So just ensure that you have done it, or if you still have doubt or if I have answered something else you were expecting, you can talk to me later. Pradyumna sir.
Yeah, sir. Thank you, sir.
Yeah, yeah, okay. So Naman, you can go ahead.
Yeah, I was muted. So I was saying that it may not be the case that not all the models may classify the data correctly or regress the data correctly, right? Not all the models would be suitable for your data set. So, and many times this is not very intuitive. Sometimes it is, like considering your data, decision tree should really do a good job. So when it's not intuitive, we just go with whatever, we just try to use different models and see which one predicts correctly and robustly. Okay, so we did this optimization and we got a correlation of 90%, which was actually less than what we got from linear SVM without optimization. That was 91%. And this can be the case. This can happen. There can be several reasons behind this. One of the most prominent ones would be the number of iterations I perform, because here it was limited to 30. You may want to do more iterations, and after doing say 100 or 200 iterations, it gets to a better, it gets to a lower mean squared error and a better accuracy, better correlation. So similarly, you can see the predicted versus actual plots for this results. I think this won't show anything. Yeah, so this is the kind of cannot really see anything from here. Everything looks good except for these two outliers. I will call them outliers because I don't think they are good data points. I don't think they are. They must be just noise because they don't make sense. Or you can have another comment that it doesn't work at very high values of the house value. But this must be outliers in that case, because otherwise we have a really good collimated prediction. So that's it from my side, I guess. You can use more of this. You can do linear regression in Matlab as well. This is something I wanted to show maybe, but I think it doesn't matter now. You can do linear regression. You can use trees that we did, support vector machines that we did. You can use Gaussian processes, which you can learn more about and then use. You can use back trees, ensemble trees method, that is many trees together. And then you have neural networks. But I would always say neural networks, of course, are really good, but should only be used when your problem is more complicated than this machine learning algorithms. If these algorithms cannot solve your problem, sure, go for neural networks because it will have uh, layers of parameters, estimation, and constraints, and it will do a much better job. It is more complicated, more time consuming. So that is also, neural network is also something that you can use for regression problems. So that's it from my side. There were a few slides, but those were anyway bonus slides. I had an idea that we may not be able to reach them, but yeah. So do we have any questions now? It's a little late,
I'm
but
really sorry that I was given you a break in between. You was continuously talking more than 2.5 hours. So
that's okay. That's okay.
I really do not have words to express my gratitude. It was really wonderful session, Naman. Thanks a lot. And I will
And
share the feedback given by all the participants, and they have given so nice comments. And even now the forum is open to all. Please encourage Naman. Please give your feedback over here. We will really appreciate it. And if you have any doubts, you can ask, and then I will conclude. Thank you.
yeah. Also, because I'm pursuing a PhD, I will have to give many more talks and presentations. So let me know if I presented it nicely and where I can
Yes.
improve it. Your feedbacks in
And
any matter,
I feel
any regard would be
fortunate
highly
that,
appreciated.
yes, I feel fortunate that you were my major and minor project student. That was really good learning
Thank you so
when
much.
we have worked for like more than last 2.5 years.
Yeah.
So now forum is open to all. You please share your comments so that Naman will get encouraged more. And if you
If
have
you have
any
any
doubt,
doubts, you can ask me right now. I'm available
yes.
even right now. And
So Naman, you
if you
have shared
think,
your email, right? Okay, fine.
yes. So if you do not have doubts right now, just now, and maybe you'll have doubts when you use these tools, Becker, Matlab, SciDavis, Python. So at that time, when you face some problem, you come around some issue, then you can feel free me to message me via my LinkedIn account, which is you can just search Naman Bajaj, and or you can contact me via my email, which I would prefer more, which is namanbajaj2015@gmail.com. Uh, Feel free
And
to
one more
contact me
thing is
anytime.
that we have created one laboratory on ResearchGate, which is related to numerical methods
Yes.
and computer programming, where we are uploading the assignments and their solutions solved by COEP students, both manually also and by using programs also. So you can visit or you can subscribe to that lab, which is there on the ResearchGate under my profile. And even the today's recording will be shared on my YouTube channel. So you can share it to everyone. So please, now please, I request everyone to share your feedback here, some of you maybe, and then I will
And
conclude.
yeah,
I would
and I
like
think
to
the
extend
presentation will
my,
also be uploaded on ResearchGate. So if you want to have another look at this presentation, we will make it available via ResearchGate.
I would like to extend my thanks to faculty members across Pune University and various colleges who have really supported this activity and attended throughout the session, like more than 2 hours. I want to extend my thanks to all the faculties. Thank you so much for attending this session and encouraging us. So you can share your feedback.
Hello, sir. Good evening to all.
Good evening, sir.
I'm Assistant Professor Dinesh Sarunke from MES College of Engineering, Pune. I would like to thank Dr. Abhishek Patange sir and the Mr. Naman Bajaj for giving such a nice information about the regression analysis and hands-on session. So such a great, just I would like to add one thing. Naman, can you please take a next session about the regression analysis in the Matlab?
Okay. A more focused on Matlab session.
Yes, Matlab and the Minitab.
Okay. I haven't actually used Minitab. These are the four
Naman,
tools that I
actually, the
generally
thing
use.
is, Dinesh is talking in regards with PhD scholars because many of the PhD scholars they use Minitab software for their
Right.
analysis. So that is
I
why
think
he
that is
and
something, sir, you use as well.
yeah, correct. So let us just think like if time
Yes.
permits and if we get
Yes,
then we will definitely do
That is
it.
a good suggestion. We can do more on MATLAB
Yes,
and
yes.
maybe also Python because Python is available to anyone and everyone, even outside the academia. MATLAB is not available to everyone. So, and Python is a smaller software with very diverse options available. So even we can maybe include that as well. Thank you for this suggestion, sir. We'll surely try to incorporate this.
okay.
Yes. So anybody would like to give more feedback? Okay, so I would like to conclude the session. I really want to appreciate and express my gratitude to my beloved student. We are working for last 2 and more years in COEP for major projects and for minor projects as well. We have published near about 5 to 6 papers in SCI and Scopus Index Journal. So I would like to express my thanks to Naman for delivering such a wonderful session. And we really expect in near future that we will conduct such more sessions which will be helpful for students and the faculties as well. So thank you so much, Naman.
Thank you.
All
Thank you
the
so
best
much, sir,
for
for
all
having
your
me here. And thank you everyone to attend, to join in and attend in such large numbers. Uh, this is probably the biggest talk I've had given. So, yeah. Thank Thank you so much, everyone, for
Thanks
joining
to,
in, and
thanks
thank you for
to
listening.
third year mechanical engineering COEP students as well, because attending webinar after 6 o'clock till 8:30 is really tiresome because they have really busy schedule. I hope, Naman. So thanks to them also.
Yeah,
We will see you soon. Keep updating us, and you can
definitely,
connect
sir.
us on LinkedIn or ResearchGate or on our
Yes, yes.
emails. Thank you. Thank you so much. Thank you.
Yeah, for any doubts, please contact me. And for anything in general, you can just contact me regarding astronomy, tool condition monitoring, regression, classification, anything. Okay. Thank you. Bye bye, everyone.